You know that big yellow school bus, right? It's such a normal part of the day for so many of us. Seems simple enough. Bus shows up, kids hop on, off to school they go. But, and this is the cool part, behind that simple routine is this just huge logistical puzzle. And today, we're going to unpack exactly what that looks like. So, you're probably thinking, come on, how hard can it really be to plan a bus route? And honestly, that's what I thought too. But it turns out this is actually one of those classic, super tricky problems in math and computer science. And, getting it right or wrong has massive consequences for everything from budgets to safety. Okay, so there's an official name for this puzzle. It's called the School Bus Routing Problem, or SBRP for short. And really, what it all boils down to is this. You're trying to create the absolute best routes you can, but you're also juggling a million different rules. Things like how many kids can even fit on the bus? And really importantly, how far should any kid have to walk just to get to their bus stop? So, why are we talking about this now? Well, it's because of this really cool new study that just came out. A team of researchers in Brazil decided to tackle this exact problem head on. And their work is like the perfect peek behind the curtain, showing us how people are actually solving this thing out in the real world. All right, let's stop talking about this in theory and get down to brass tacks. We're going to zoom in on one specific place, Fortaleza, Brazil. This is where the researchers put their ideas to the test with a real public school. And believe me, they had some unique hurdles to clear. So what kind of hurdles are we talking about? Well, for starters, the city's street grid is kind of messy. It's not a nice, neat grid, so some places are just plain hard for a big bus to get to. Then you've got local regulations about who even gets to ride the bus for free. And to top it off, all their buses are the exact same size. Now, you might think that makes things easier, but it also means there's a strict, non-negotiable limit on how many kids can be on any single route. And all of this leads us right to the central conflict, the big question at the heart of the whole thing. It's a classic problem you see everywhere in public services. How in the world do you save money and at the same time make sure you're being fair to everybody? So the researchers basically set up this tug of war between two main goals. In one corner, you have the efficiency goal. This one's pretty simple. Drive the fewest miles possible, right? Less driving means you save money on gas, on bus repairs, all that stuff. But in the other corner, you have the equity goal. And this is all about minimizing the maximum distance any one kid has to walk to a bus stop, because that's a huge deal for safety and just basic access. And check this out, because this visual really shows you what's at stake. Look at the routes on the left. Those are planned just to save money. See how direct they are? Now, look at the ones on the right. Those are designed to make sure no student has a crazy long walk. And you can see the bus routes themselves get way more complicated, which means they cost more to operate. So that's the key takeaway here. You can't have your cake and eat it too. You can't get perfect efficiency and perfect equity. You've got to find that sweet spot in the middle. So the big question is, how did they find that balance? This is where things get really, really clever. They came up with a solution that's both super smart and actually works in the real world. Let's dig into how they pulled it off. Okay, first thing you need to know, with a problem this messy, finding the one single perfect answer is, well, it's pretty much impossible. I mean, the number of possible route combinations is just astronomical. A computer could run forever and not check them all. So instead of trying for perfection, they use something called a meta-heuristic. It's a fancy word, but all it really means is a kind of smart, intelligent trial and error. The specific algorithm they used is called GRASP-ILS. Let me break down how it works in a really simple way. Think of it like this. Step 1. The computer makes a solid first guess for the routes, a pretty good starting point. Step 2. It shakes things up. It messes with that first guess a little. Maybe it moves a bus stop from Route A over to Route B. Step 3. It looks at that new, slightly messed up route and tries to fine-tune it, looking for tiny improvements. And step 4, and this is the key, it does this whole process again and again and again, thousands of times. And the whole time it's keeping track of the absolute best set of routes it's found so far. Okay, so after all that complicated computer science, did it actually work? Did it make a difference? The answer is a huge, unqualified yes. We're talking better routes and, at the end of the day, a much better experience for the students. Get ready for this number. The algorithm found ways to plan the routes that cut costs by up to 35%. Let that sink in. 35%. For a public service like a school district, that is an absolutely massive amount of savings. That's money that can go right back into classrooms or teacher salaries or anything else. And it's not just about the money, not by a long shot. The researchers make this great point. When you have better routes, you're burning less fuel. That means lower carbon emissions. It means the whole system is more reliable and just works better for everyone. It's a win-win-win. A win for the taxpayers, a win for the students, and a win for the environment. You know, when you step back, this is so much bigger than just school buses. It's really about using smart, data-driven thinking to fix the everyday systems all around us, to make them work better for all of us. And that kind of leaves us with one last big question to chew on. If we can use math to build fairer, cheaper school bus routes, what other big, important public service should we point this kind of thinking at next?